We're starting with section 1.5 now in this more or less the second half of this chapter 1, carrying and canceling units. We're going to talk about the grid method. This is very important stuff so that you can begin to do your homework assignments. We're just going to solve a simple problem. How much power does it take to ride a bicycle at 20 miles an hour? Now, I think that this is actually an underestimate, as we talked about in class the other day, because it's not accounting for any drag. But if you were to apply 4 pound force to your bicycle, if that's the power or the force that you were applying when you ride your bike and you were going this fast, and the power would be just the force times the velocity. And so what we'd like to do, since these units would be kind of messy in pound force miles per hour, that's kind of messy to deal with, we're going to convert these to SI units where things work out a lot better. So we have a number of conversion factors here that are being multiplied by this product here. So if we go to the next slide, we can see that each of these conversion factors looks like this. And so in fact what we have is we've just solved a simple equation. We've taken 1 meters per second here equal 2.237 miles per hour. And we've divided both sides of that equation by 2.37 miles per hour. And what we get out of that is we get 1 on the left-hand side. And we can multiply 1 by this product, force times velocity, as many times as we need to get the units right, because 1 is not changing the product. So we're not changing the actual thing that we started with, the force times the velocity. We're just multiplying it successively by 1 to convert the units. And as you can see, the miles per hours cancel, the pound forces cancel, the newtons cancel, the meters cancel, the seconds cancel, and all we're left with on the end here is watts. So everything cancels in the grid method, and when you multiply all the numbers out, you end up with 159 watts. So this is actually kind of a two-step process. When I teach this, I always say you're dealing with 2 things here. You're going to deal with numbers. You're going to basically multiply and divide and do whatever sort of math you need to do. You're going to deal with the numbers. But you're not done until you also deal with your units. So it's a 2-step process. You must do both. And in fact, I've listed this as being a very important section here. This you can see that I've labeled this, if I can do this, very important, because of the fact that I want your homework to look like this. When you have numbers to deal with and equations to deal with, I want them to basically look like this. You should not skip any steps. All steps should have units on the numbers. That means that this is the type of thing that I'm looking for in your homework assignments when you have to basically cancel units and deal with equations. Okay? So that's what we're all striving for. So that's basically what we're getting at. The other thing that someone asked in class is whether all steps need to have numbers or units on the numbers, and I said yes, they do. My point is that this, and the point that I made in class, everybody kind of knows what I'm getting at here when I put 9.8. We're thinking that this is likely to be the acceleration of gravity, but this is not the acceleration of gravity. This is merely a number. This is the acceleration of gravity when you have the units on it as well. This is going to be g. This is not g. So units, numbers and units, deal with them both. Okay, now when we're dealing with traditional units, we end up having some difficult things to deal with. And there are various ways. This is from the book, some conversion tables, table F1. And we can see some familiar conversions up at the top of the chart here. If we look here, we've got, 1 meter equals, a little bit over 3 feet and so forth. And so 1 foot equals 12 inches. And these are things that we're familiar with. When we get down here, we've got some more difficult things to deal with. All of a sudden, we're seeing pound masses and slugs. And so we need to be able to convert basically between SI and traditional units. And this is fairly easy to do if we stick to the grid method and stick to the conversions. So if you're trying to convert 1 kilogram to a pound force, you're going to use this conversion factor right here. If you're going to have to use slugs, you're going to use a different conversion factor from kilograms to slugs. You're going to take 1 kilogram equals 1 slug divided by 14.59 and so this is how we have to remember that slugs and pound mass are units of mass. The other difficult thing in transitioning between SI and traditional units is to deal with pound force, and we can see a similar type of conversion factor. 1 pound force equals 4.448 newtons, but it also equals 32.17 pound mass foot over second squared. And I wanted to make a point here that the book does, that there are some definitions here. Whoops, let me grab the pencil. 1.0 newtons, or 1 newton, is going to equal 1 kilogram times 1 meters per second squared. So that's a definition, actually, 3 bars. It's also a definition that 1.0 pound force is defined to be the amount, defined to be the force necessary to move 1 slug at a rate of 1.0 feet per second. And in addition, 1 pound force is also defined to be the amount of force that you get when you basically exert or that the force that is exerted by a 1 pound mass accelerated at a rate of 32.2 feet per second squared. So you can see in these two cases that the accelerations are different. And so these are just defined, these masses, the slug and the pound mass, are defined to be differently. So I will guarantee that somewhere along the course here, throughout this course, somebody will have their answer be off by a factor of 32.2. I've seen it when I've taught this course before, and that's just going to be the case. So be careful. Remember that a slug is different than a pound mass, and that you may need to do a conversion here and realize that these are defined differently. Now, one thing that I wanted to show you now, interestingly, is that let me go back and redo that, get the right pencil here. 9.8 meters per second squared. If I multiply that by 3.281 feet per 1 meter, this is a conversion factor. Again, this conversion factor equals 1. This actually equals 32.2 feet per second squared. So this quantity here is the acceleration of gravity, just like 9.8 meters per second is. So pound mass is actually provides a 1 pound force if it's being accelerated at the acceleration of gravity. So pound mass is kind of a tricky definition for mass. But remember, when dealing with these masses, you can stick to the conversions, and if you do use your grid method correctly, and paying attention, very close attention, when you're dealing with traditional units in force and mass, you're going to be able to get the right answers. So here's what I was just saying before, that a force of 1 pound force is defined as a force that will accelerate a mass of 1 slug at this rate, 1 foot per second, and 1 pound mass will be accelerated at 32.17 or 32.2 feet per second. Okay, so let's move on to the next topic, which is the ideal gas law. This we saw before earlier in this chapter that a gas is a fluid, and so we need to have a way of dealing with basically the ideal gas law that relates the pressure, volume, and temperature. So it's a fundamental property of a gas that's going to be a relationship between pressure, volume, and temperature. I'm not going to go through the derivation. You can see that in the book. It's not that important for the course. It's important to know how to apply the equation, but it's basically was a combination of something called Boyle's law and Charles' law, which came about by assuming either constant, I believe, constant pressure and constant temperature. And these were laws that people understood about gases before it was combined into the ideal gas law. They combined it also with Avogadro's hypothesis, which dealt with the amount of molecules in a mole. And lo and behold, they come up with the what I learned in high school chemistry was PubNert, an acronym, or basically a name for this equation. And PV equals nRT, but you can also write it in different ways. You can divide through by the volume, combine that with the mass. If you pull out, if you apply R to B to your particular gas. So this is the universal gas constant, but if you pull out, if you combine that with with N and pull out the mass from that, you get the gas constant here for your particular gas that you're dealing with. So it's R, not R sub U, and so then you get this equation. I'm going to just skip ahead 1 minute and say that there are various forms of this equation. The density form has the density here. The mass form divides back out that volume, gets the volume back on the other side. PV equals mRT, and again, R now is the specific gas constant for the gas under consideration. But this is important when you want to find the mass of the gas. And then this is the traditional PubNert equation that has the number of moles and the universal gas constant in it. And this is also an equation that relates R to RU. And so typically in this course, we're going to use the top two. We're either going to be interested in density or mass or pressure or temperature or volume, but we typically will not use the mole form of the equation. So if we go back some practical applications of this, one of the things that I said that I've told a story about when I was flying to Greenland last summer. They had a tank of liquid nitrogen on this aircraft, and they had a vent for the liquid nitrogen because as the plane was flying and when it was kind of rough air and turbulent, the liquid nitrogen would slosh in the tank, and it would develop. It would basically vaporize into some gas, and it was the pressure gauge was going up, and the load master on the cargo flight I was on was getting frightened about the gas pressure going up. But as long as that was being vented to the outside of the aircraft, which it was, there was no problem. But of course, why is this necessary? It's necessary because if it wasn't properly vented to the outside of the aircraft, the pressure could build up and the tank could explode and be a problem for the passengers that were in the plane. in addition to the crew. Another example are blowdown valves that they have for boilers that have a boiler that may be providing steam for heat. I know at the University of Idaho they use steam for heat, and so you have to have safety valves on these boilers in case the gas pressure gets too high. So let's do an example problem, and we're going to use the. Let's just read through this. I would encourage you to take a look at this problem in the book, because it kind of shows a step-by-step method of how to solve engineering problems. It has a good example of how to approach a problem like this. So it says find the total weight of a 17 cubic foot tank of nitrogen if the nitrogen is pressurized to 500 psi. Now, one thing that we haven't talked about yet is what this A means, and A means in this case pounds per square inch absolute. So this is relative to atmospheric pressure. We'll talk about that later, but basically we're just going to pressurize the tank to that amount relative to the atmosphere, the local atmospheric pressure. The tank itself weighs 50 pound force, and the temperature is 20 Celsius. So we're going to need to combine this pressure and this temperature in order to find, since we know the volume, we're going to be able to find the mass. The mass is the only thing we don't know, in other words, in the ideal gas law. So we've got the weight of the tank is going to be, if we basically use a conversion factor, this is 222 newtons. We've done a couple of other things down here. We've determined that 17 cubic feet is about almost a half a meter cubed, and our pressure equals 500 psi. If we convert that into pascals, it turns out to be 3.45 megapascals, or 3.45 times 10 to the sixth. And our temperature, remember, these need to be in absolute temperature. These need to be in Kelvin when we're using the ideal gas law. So I should make that point back here, that if I can find it, no, too far. Note this right here. I'm going to draw a red line under that for sure. Right here, you must use absolute temperature. This is another common mistake. Use absolute temperature. It's got to be in Kelvin. So if you're in Fahrenheit, Celsius, or Rankine, or any other kind of strange temperature unit, you need to convert to Kelvin. So you can see that this was done here in this problem, and we're in good shape. So let's go forward. Oh, another thing that we need is the gas constant for nitrogen. Since the gas inside the tank is all nitrogen, we can look in table A2, and we see that nitrogen has an R value of 297. And this is a tricky unit here. This is one thing that I consistently see in this book that I disagree with. These units this actually equals 297 joules over kilogram Kelvin. The Kelvin is actually in the denominator. These brackets are not in the right places, so be careful of that. The bracket should be here, not where they are. So be careful, and if you use these units, you would notice, in fact, that they don't come out right in your final answer in the grid method if you used what he has listed there. So let's get a new page and let's solve this problem. So what we want to do is we want to use that's the volume, pressure times volume. We're going to use the mass form of the equation, and we're going to have R nitrogen times the temperature. And we're going to solve this for the mass. That's what we want. The mass of the nitrogen is going to be the pressure over the volume over the gas constant for nitrogen times the temperature. And we've already got all the pieces from the slide before. So we have the pressure, 3.45 times 10 to the sixth. That's newtons, and those are over meter squared. That's what a pascal is a newton over a meter squared. The volume is 481 meter cubed, and that's just over 1. There are no units in the denominator. I'm going to continue on down below here. We're dividing by 1 over r, so we're going to have 297 in the denominator, and that's joules per 1 kilogram Kelvin. And this was a joule, but a joule is a Newton times a meter. And then finally, all we have is the temperature, just 1. It's 1 over the temperature, actually. And so this is our equation. If we multiply out, we can see that we have a large number here, 3.45 times 10 to the 6th. We're going to take about half of that, but then we're dividing also by 297 times 293, so this is actually a pretty large number too. And if we do, remember the two-step process, do your numbers, then do your units. So if we calculate this, we get 19.1 for the numbers, and now let's see what we're going to do with the units. I'm going to grab a red pencil, and this Newton cancels that Newton in the denominator. This meter squared and this 1 over meters, this is 1 over meter squared and 1 over meters, cancels these two, or it cancels this meter cubed. And this Kelvin cancels that Kelvin. Everything else is gone except for what? Kilograms. So our final answer is in kilograms. 19.1 kilograms. Now we're not done, because that's not exactly what we were asked for. We were asked for the total weight. And the total weight is the weight of the tank plus the weight of the nitrogen. And in fact, we don't even know the weight of the nitrogen yet, because we only have the mass. But we know that the weight of the tank was 222 newtons. And we know that this is going to be just the mass of the nitrogen times the acceleration of gravity. So this is going to be, I'm going to give myself a little bit more room here, plus 19.1 kilograms, sorry for the mess there, times 9.8 meters per second squared. This turns out to be 187 newtons plus 222 newtons. And what we're left with is 409 newtons for the total. What's interesting is at that pressure, the tank, the weight of the gas in the tank is almost equal to the actual weight of the tank. Okay, so that's how we apply the ideal gas law. The conditions under which the ideal gas law are valid, you can see here. For gases near atmospheric conditions, the ideal gas law is going to be a good approximation. So for atmospheric calculations, we can normally use this equation. And when both the liquid phase and the gas phase are present, we can consult a table, basically a thermodynamic table, to find the density of the gas in the gas phase. But when we have a situation where we have very hot gases, say the exhaust of a rocket, gases can ionize and dissociate, and at that point we're going to be having an invalid, and we're going to have an invalid ideal gas law. So the ideal gas law will not be able to be applied for very hot gases. For any of the things that we're doing in this class, we will assume the ideal gas law. We're not going to do any special cases of strange gases, ionizing gases. So determine if the gas can be characterized with the ideal gas law. One can calculate the compressibility factor, and we'll talk about that in Chapter 2. And in fact, this was a question that a student had a couple days ago on Wednesday, was whether or not or what sort of limits are placed on these things. And certainly we do have limits for deciding when things are valid and when they aren't. So, a couple other things in this chapter. Just quickly, the Wales-Wood model is something that the author uses throughout the book. And this is a very good approach. If you have a hard time starting engineering problems, if you're still struggling with that after statics and dynamics, this is good practice. This book will give you lots of good practice. And I don't want to belabor this point right now, but there are basically 6 steps. You define the situation, which is really just a restatement of the problem. You state the goal. What is the quantity that you're trying to find? You generate ideas. How might you go about solving for things that you need that you don't have? Once you kind of start to get a picture from generating the ideas of the things that the steps maybe that you're going to need, then you can make a plan. Like, I'm going to do this first, then that, and I'm going to add this to that and multiply by this. And then once you have a plan, you can take action and execute your plan in order to get your solution. It's always important to review your solution and the process to make sure that your answer makes sense and that you're getting a quantity that has the right units and about the right magnitude. I also very much encourage students, if they've got a problem, especially on an exam, if you get an answer that's, a million times larger than you think it should be, write it down. Put it down on your exam. I cannot give you any points if you don't show me that you understand that the problem is wrong. That is a critical point. And you will get points if you have a wrong answer, but you know it's wrong and you explain why you think it's wrong. So the final topic. So in summary, I guess you might take a look at this, and all of the problems in the book follow this Wales-Wood model, and you will see how Dr. Elger has implemented this in the textbook. It can be useful. So finally, when the primary, let's look at dimensional homogeneity. We'll return to this, I think, in chapter 8. When the primary dimensions, remember these are the dimensions that are like the fundamental dimensions, the SI dimensions, the mass, length, time, temperature. When the primary dimensions of each term of an equation are the same, the equation is dimensionally homogeneous. And you're going to do a problem like this in your homework to show that the terms, to determine if the terms in the Bernoulli equation actually are dimensionally homogeneous. And we'll just do a simple example of this. So let's take the ideal gas law. So remember what I said in class, that when we're looking at the units of something, we put it in square brackets. So let me just start this over again. The ideal gas law is the form of it that we're going to use is the density form. Okay. And I'll start a new sheet of paper and I'll say, let's just take the first side of that. From table A6, we find out that the primary dimensions of this, or the dimensions of this are made up of these primary dimensions: mass over length divided by time squared is pressure. And so let's determine whether or not the other side of the equation, the other term in the equation, is dimensionally homogeneous with this. So we're going to write this. We need to find out what the dimensions are of each part. Okay, and so what are the dimensions of density? It's mass over length cubed. R is a bit more complicated because it is it's basically a joule, a joule per kilogram Kelvin. And so a joule is a Newton, which is mass times length over time squared, times another length. So we'll just go length squared here. And that was divided, if you remember, by kilograms and Kelvin, which is given the symbol theta. So this is basically your joule. This is basically your kilogram over Kelvin, and then temperature. The third, this guy right here, is going to be temperature as well. So let's go through and cancel. we've got the temperatures cancel, one in the numerator, one in the denominator. We've got this mass canceling that mass, and we've got 2 of these lengths canceling 2 of these and leaving 1. So what we are left with for the dimensions of rho, r, and t are mass L, just counting up what's left, t squared. And we can see that we have proved that these 2 dimensions imply dimensional homogeneity, or what we sometimes abbreviate as DH. So we have proved that the ideal gas law is dimensionally homogeneous. And you'll be doing this for the Bernoulli equation on your homework. This is important when we start to talk about dimensionless groups, and I'll just throw this out here now, and we'll return to this later on in the semester, that a dimensionless group is any arrangement of variables in which the primary dimensions cancel.